Now we're going to do a quick little intro to an application of this. All right. So the idea is that if we think about velocity, all right, as something that is the rate of change of a position, and they give us a position function, S of t, all right, we can actually use this same idea to come up with a reasonable explanation or definition for the instantaneous velocity of a given object at time t. Okay, so we're going to do this by first calculating the average velocity. And average velocity, again, is just the idea is looking about to slope. It's the same idea as the slope formula we just used. But we're looking at the change in the y. So this is the change in the distance of the object over the change in the time. Okay, and what you're going to find out is that as we do this more and more, right, as your points get closer and closer, we're going to be getting to something that is called a limit. Okay, and that's ultimately what this unit is about. So even though we're just kind of doing an intro, that's essentially we're introing this idea of taking a limit. Okay, so I'm going to use this information to calculate the average velocity of this rock that is dropped from a height of 64 feet. Again, they're giving me a position function, S of t. They're giving me the time interval, so from 0 seconds to 2 seconds. And we're going to find the average velocity of this rock over the given intervals. Okay? And this is going to give us information to guess. Right now we're just guessing, right? Later on we'll find the exact answer. But to guess the instantaneous velocity of the rock when it's been a half a second since it's been dropped. Okay? So we'll start with the first one. So we're going to use that formula from the previous slide, right? The average velocity, I'll put it above this here. The average velocity is the change in the position of your object relative to time, right, over the change in time. All right, so just copy that formula. So we have the change in our second one, right? If we have this one here, it's going to be S of 0.5 minus S of 0.49 over the change in that time, which is just 0.01 seconds. Okay, we can go to Desmos here to get our y values. So I'm going to plug in 0.5 for t, and then I'm going to plug in 0.49. So we have all right, here we go. Negative 16 times 0.5 squared, and then I think it's plus 64. Confirm. So that one is 60. All right, so that is our position here is 60 minus, now we're going to plug in 0.49 for t. That's going to be 60.1584. Okay, and that's all over 0.01. So if we do the math here in Desmos, we'll subtract 60 minus 60.1584 divided by 0.01. We get our average velocity over that period of time of 0.01 seconds is negative 15.84. Okay, negative 15.84. Okay, and this is feet per second. Always want to include units. Okay, now we're going to do the same process, but this time we're going to be using 0.5 to 0.51. So it's the same time interval, but just on the other side of 0.5. So now it's going to be 0.51 minus S of 0.5 over 0.51 minus 0.5. So same time interval, right? 0.01, that's no different. And we know what happens when you plug in 0.5. We got 60. So the question is, what happens when you plug in 0.51? Okay, so plugging in 0.51. And I know I'm showing this over again, but when you're doing this with your Chromebook, if you want to just plug into one of the first ones that's already there, it's a little easier. 59.8384. Okay, so same math I'm going to do in Desmos to find the average velocity over this time interval. Subtracting 59.8384 minus 60. All right, let me move this. So we have 59.8384 minus 60 divided by 0.0. Negative 16.16. That is our average velocity over that interval. So negative 16 I already forgot. 16, the same number, feet per second. Okay? So these are the average velocities. So velocity average. And it says to estimate or guess the instantaneous velocity of the rocket, time being half a second after you dropped it. And if you notice, we went just below 0.5 seconds, right? Part A was just below 0.5, and part B was just past 0.5. So the idea is it should be somewhere in between. If I look, negative 15.84 and negative 16.16, they're both 0.16 feet per second away from negative 16. So I would guess that the instantaneous velocity, so I'll put velocity instantaneous, my guess would be that it's negative 16 feet per second. And again, we'll show you later on in this course how we can do that specifically or exactly instead of just guessing. Okay, the last question, all right, or the second question, I should say, from the beginning slide was the area problem. So essentially, this is, when I think of calculus, this is the classic question or the most often idea that we talk about is if you have a curve, all right, and you want to look at the area under that curve over an interval. So in this case, we're looking at the area between A and B under this curve f of x. All right, so the most basic way to do this is to kind of slice up that area into shapes that we know how to calculate the area of them. So you notice in this figure 2.9, we've taken that shape and we sliced it up into small rectangles because we know how to find the area of those rectangles. And essentially what this is introducing you to something called integral calculus. So the first question about the tangent line let me start over. The first question that is about a line that is tangent to a curve at a point, that is the derivative idea, and that's getting into differential calculus. And this question about the area under a curve is into something called integral calculus, okay? So let's look at one more example together, and then we'll be finished. All right. Again, I'd encourage you to read the textbook, read this section in the textbook, read the pages that I'm going to post or posting on from the book, Calculus for Dummies. Anything you can do to help your brain understand this, besides just listening to my lectures, is really going to help, okay? Especially as you prepare for the exam, and then obviously when you go to college. All right, no matter what you end up doing in college, if you're taking calculus, you're going to end up needing to refer to your own resources. You're going to find out in college, and that was my experience as well, is that yes, professors have office hours, but so much of your time is going to be spent working on how to figure this out on your own. Okay, so we have a function, another quadratic. This time they've just shifted it 1 unit up, and we want to find the area between 0 and 3 that's under this curve. And they've estimated already by making 3 rectangles. So if you look here, we know the area for a rectangle is length times width. So if you look at all of these lengths here, all of them are 1. All right, so for the first triangle, it's 1, second one, and the third, they're all 1. But now if we look at the width, that one is 1, this one is 2, and this one is 1, 2, 3, 4, 5. All right, so this one is actually 1 square unit. This one is going to be 2, 1 times 2, and this one is 1 times 5, which is 5. So to estimate this area, if I were to estimate this area, I would add 1 plus 2 plus 5 to give me 8. Okay, so I'm assuming here that the 8 squared units is the area that's under this curve. Okay, again, this is just a basic intro here, nothing too intense, but again, try to read as much as you can. Okay, so that does it here for this video, for this preview of calculus.